Okay, this is our 15th physics lesson on friction. We're going to learn about the difference between static friction, and kinetic sliding friction, and kinetic rolling friction. We're going to be able to solve for the force of friction. We're going to be able to solve for the coefficient of friction, and we're going to be able to determine net force and acceleration when friction is involved, and then use that net force and acceleration to determine other variables like maybe a VI or VF or something like that. Okay, so the key here, we're going to use these equations today. I will talk more about this later, but for now I want to just mention, anytime you see an F in all these equations, you know that unit is going to be newtons. So just be aware of that. Anytime you see a mass, watch out, remember that is kilograms. A lot of the weight scales lie to you. When they tell you kilograms, they're telling you your mass, not your weight. Force of friction is a friction caused when surfaces rub against each other. If you take a look at on a microscopic level, you're going to have rough surfaces, and they're not going to want to go across each other. And they're going to be in the opposite direction of motion. So if you take a look at this, the motion, if you're trying to push it to the right, the friction itself is going to be to the left. Static friction is caused by applied force when an object is not moving. So if you take a look at this guy pulling or pushing this object, I guess he's pushing because he's going, the applied force is to the right. It's not moving. So as he pushes, you build up more and more frictional force, but it'll be static frictional force because it's not moving. Whereas kinetic frictional force, when you have sliding going on, then you're going to have kinetic friction because there's going to be moving friction. And just notice a little bit about how close that these surfaces are versus those surfaces. This is going to lead into kinetic frictional forces always being a little bit less than static frictional forces. Rolling frictional forces, kinetic rolling frictional force is just when a surface is also in contact, but it's also rolling. We're going to use spring scales to determine some of the forces in the little and what we're doing today. And what a spring scale is, it just has its own little spring in there that if you pull a certain force, it can read it based on we'll talk about Hooke's law later on in the spring constant. The spring constant causes it to read somewhat accurate the amount of newtons of force you're applying. Until motions, surfaces have static friction. So at the beginning, before the motion occurred, right around here, we have static friction going on. But once motion occurs, everything past that, everything beyond that is going to be kinetic friction. So once moving is occurring. General rule, kinetic sliding friction is less than static and not moving friction. And once again, that is because of the surfaces much closer here, whereas here you have a little bit of spacing, a little bumping against each other, but it's going to be easier to keep something going than to start it going in the first place. Rolling friction itself is going to be the least of all of them. So here's the first question. What type of friction do you have when an object is not yet moving? And that's going to be static friction. Second question. Place the following in order from greatest possible force of friction to least. And let me just tell you this note right now. We're going to often just call kinetic rolling friction, and static friction is always just going to be static friction. But when we say kinetic friction, we're usually talking about sliding friction. So just watch out. From here on out, anytime I say kinetic, I'm talking about sliding friction unless I say kinetic rolling or just straight up say rolling friction. So it would be static friction first, the greatest amount of friction. Then we have kinetic friction, sliding friction, and least would be the rolling friction. Looking at the force equation, FF stands for the force of friction, and this is related by the thing called the coefficient of friction. This just is a number that has no unit that relates how much force there is when the normal force is there. When the ground, so the ground is, you have weight pushing down, you have the ground pushing up. And so we'll see this normal force will change, whereas weight won't change. And normal force is actually the value that we need to use when we use the force friction equation. And this symbol is called mu. It's like a little mu Greek letter, and that's what we're going to use there. And don't be often students will mess it up because it's such a long word for such a little variable. Coefficient of friction. So on a horizontal surface, the magnitude of normal force equals its weight. So you might be given weight in a problem, and if you're given weight in the problem, well, that's going to be the number you're going to use for Fn. But sometimes you're going to be given mass in a problem. So if you're ever given mass in a problem, you have to solve for weight. and weight just is equal to mass times gravity using 10 on Earth, 10 meters per second squared. And once you solve for that, so if you're given mass, just multiply by 10, and that will be the normal force. If you're given weight, you're already there. You go straight to normal force. That would be equal to the weight. Once again, magnitude of the weight. The direction is going to be different. So the different coefficients of friction, we have different values depending on if it's static friction, depending on if it's rolling friction, or depending on if it's kinetic friction. We're going to use the same equation no matter what. The only thing is that if we're looking at a table and determining the coefficient of static friction, or we know the object's not moving, well, that's going to be this mu symbol, the coefficient of friction symbol. And if we use the static friction coefficient, we've just solved for the force of static friction. And likewise, if we use the kinetic value for kinetic friction, or we know that the object's moving at in constant motion and we're using that in a lab setting, well, if we use that UK for this, I'm not going to change the equation. It's just, I would know that I'm using the coefficient of kinetic friction here, and then I would have solved for the force of kinetic friction. And if for some reason I use once again, likewise, like what I've been saying before, if I use the UR, the rolling friction here, well, I would have solved for the force of rolling friction. But we're going to use the same equation no matter what. It just depends on how we either get the data, or in the table where we, which data are we using? Are we looking at the static, kinetic, or rolling friction going on? So this is the table. This is usually an engineer's going to use a much longer one. If you're trying to determine a material to use for a wheel or some other surface, if you want to stick, slide, or roll, it's going to be important to you what kind of friction you have, what kind of materials you have. And for the sake of our lesson, we're going to go look at this table to determine the variables that we'll use when we're asked to solve for the force of friction. So a little more about coefficient of friction. The bigger the coefficient, so the bigger the number, the more resistance to the force of friction, or it's going to have more force of friction. The more resistance to motion. And for the same contact surfaces, the UK, the kinetic friction, is almost always less than the coefficient of static friction. So you take a look at this. And so between wood and wood, the static friction coefficient is 0.25. Well, the kinetic friction is less than that, so there's going to be less force, caused by friction when an object's actually moving wood on wood. And so you can use this table to kind of determine what you need. It's harder to get an object moving than keep it moving. And once again, another reason why wood on wood versus wood on brick versus rubber on concrete. Some surfaces are going to have a whole lot less, rough surface. Some surfaces are going to be a whole lot less rough. And just the way that the surfaces are formed, based on what objects are rubbing against each other, you're going to get these coefficient of frictions. Once again, some engineer and a bunch of engineers figured this out and use this for designing purposes. Which coefficient of friction would have the greatest resulting force of friction? So go ahead and answer that. And it's going to be 0.8. It's going to be the bigger number. The bigger the coefficient of friction, the more friction it is. And usually the numbers don't get much above 1, but you can get you can get a little bit more friction going on. But usually the numbers are around less than 1, between 0 and 1. So here in the animation, just to look at what's going on. Initially, you have static friction, and what I want you to notice when we get back to this, the force of static friction increases. So if I apply a little bit of force and it's not moving, it's still static friction. If I apply a lot of force and it's still not moving, it's still static friction. So it's going to increase the whole time until the motion starts occurring. At that point in time, it's going to be kinetic friction. And if I'm going at a constant velocity, I have to actually apply less force. So notice another thing about this animation. The applied force decreases right when it starts moving, because the force of friction also decreases, and this StickMan is pushing this object at a constant velocity. So calculating the force of static friction. Any force applied before the motion equals the magnitude of static friction. That just means if it's not moving and you're applying a force and it's not moving, that is the force of static friction. And no motion, the reason why, so the force you're applying, if there's no motion, that means that there's no net force, which means that the force you're applying must be equal to the force that's opposing that motion. Once again, the negative in this just means in the opposite direction, which you see in the arrows. So here's a problem. What's the force of static friction when there's 3.5 newtons of force when 3.5 newtons of force is applied horizontally and the object is not moving. And it's just going to be 3.5 newtons. If it's not moving, it doesn't matter how much, it's going to be static friction. To calculate the coefficient of static friction, this would be something you might do in a lab. And if you're in my class, I'm going to have you do this at some point in time, either with animations or in a lab setting. But you want to maximize the force while this object's still not moving. So let's look at the spring scale a little bit closer. Notice how it gets to 1.0 newtons and then it kind of flings back and goes to 0.8 newton, around 0.8 newtons before it starts moving. So you look at the moment, like right here, right the moment you look at this reading, right when it starts moving, and it gets to 1.0 before it ever goes back down. Well, that is going to be the maximum force required to first start that object moving, and so that's going to be what you're going to use to solve for this coefficient of static friction. So we'll use that force of friction in the coefficient, or in the force, we'll use that that value for the force of friction. That's going to be our FF in the coefficient of friction equation. So let's go ahead and give you an example. A 0.4 kilogram block is sitting on a surface. What is the coefficient of static friction between the block and the surface? When it takes 1.0 newtons of force before the block begins to move. So once again, in a lab setting, I would have just wrote it off here, but I'm telling you right there, it's taking 1.0 newtons to get it to move. What I'm not telling you is the normal force. So you notice it's a horizontal surface, so you remember from earlier in this lesson, if you have a horizontal surface and you're given kilograms of mass, you have to figure out the weight. And when you figure out the weight, so 0.4 kilograms times 10, you figure out the weight, the magnitude. So once again, the direction will be different, but the magnitude of normal force will equal to the force of the weight force in this case. So the ground's pushing up by 4 newtons, and that's what's going to lead to the friction. So the force of friction is equal to the coefficient of friction. Once again, you look at it, and they want you to solve for it, so you're going to have to rearrange that equation. So you divide the Fn by both sides, you get coefficient of friction equals force of friction over the normal force. Plug in our values. Once again, the normal force, or the force of friction, was the one we got from reading the spring scale, or also it gave it to us. And then the normal force was this right here, which we solved for. And we get a coefficient of friction of 0.25. And this would be the coefficient of static friction because we took the value before the motion actually occurred. Calculate the force of kinetic friction in a lab setting. So to do this, we want to create the situation of dynamic equilibrium. We want to keep this block moving at a constant velocity, and we don't want this spring scale to be jumping back and forth. We want it to be kind of sitting around one spot. And when it's sitting around one spot, we know that the force that we're applying must be equal to the force of friction. And that's going to be the force of kinetic friction we're going to use to solve for, that we would solve for the force of friction. So here's an example in a second. So this one, just in this example, it stopped at 0.8. Once again, this is kind of a continuation of the last one. This is after it's already moving. So it stopped at 0.8 newtons, and that's going to be a force of friction that we're going to use, or that's going to be our force of friction that we have here. What's the force of kinetic friction when 1.3 newtons of force is applied horizontally to keep an object moving at a constant velocity? And that's just going to be, if it takes 1.3 newtons to keep it going at a constant velocity, that's equal to the frictional force because you're applying 1.3 newtons this way, but the force of friction is going to be net force of 0. So that means the force you're applying, which was 1.3 newtons, that's what it tells you here, must be equal to the force of friction right over here. Okay, calculating the coefficient of kinetic friction in a lab setting. So to calculate the coefficient of kinetic friction, we're going to do a lot of the same thing that we do to just determine the force of friction. We're going to measure the force required to keep this object, this block, or whatever we were trying to find the friction of. Some people like to do a shoe in the ground in the lab settings, but you're going to try to determine it when you have constant velocity going on. So you take a reading of the force of friction when you have that constant velocity. That'll be your FF that you're going to use to solve for the coefficient of, in this case, kinetic friction, because we want the object to be moving the whole time. So for this one, we take the value after it starts moving, which is about 0.8. So here we have the same 0.4 kilogram block on a horizontal surface. What is the coefficient of kinetic friction between the block and the surface when it takes 0.9 newtons, I think I changed this to 0.8 newtons of force to keep the block moving at a constant velocity? So we have Fw equals mg. We have 0.4 is our mass, 10 is our gravity. Just like before, we still have the same normal force. It's still the block on the same surface. So we're going to go ahead and solve for the coefficient of friction. But in this case, we're now going to have that, once again, the 8th. So we disregard that initial. I changed this to make it work with wood on wood. But 0.8 newtons of force required to keep this object moving at a constant velocity over the force that the ground pushes up, which is the 4 newtons. And we get a value of 0.2 as our coefficient of friction. So let's go ahead and just kind of summarize some things here. If it takes 45 newtons of force horizontally to move a wood block with a constant velocity, so we're moving it with a constant velocity across the desk, what is the applied force? If it's constant velocity, whatever our applied force, we're applying 45 newtons because that's what it tells you. You're just applying the 45 newtons. What's the force of friction? Well, because it's a constant velocity, we know that the force 45 this way that we're applying must be equal to the force of friction, the 45 that way. What's the net force? If you take a look at these, they're both in opposite directions, so you're going to have 0 net force. And net force causes acceleration, so if you have 0 net force, you are going to have 0 acceleration as a result, so 0 meters per second squared. So let's take a look. Non-zero net force causes acceleration. So if this F net, if we take a look and we might have more this way than the force of friction that way, we're going to have acceleration going on. So we would have a net force. So all that non-zero net force means is that you do have a net force. And I think I have another problem before we go and look at the acceleration. So what is the minimum force? What minimum force do you have to apply horizontally to get a 1.5 kilogram block of wood at rest and move on wood? So I'm just having you right now use this table and do another problem. So when you have this, you notice it's wood on wood. So you're going to go ahead and find wood on wood, and then you're going to take a look, apply horizontally on the block at rest, so it's at rest to move it. So it's just first moving. So we're going to go ahead and go with static friction. That's going to be important in determining what you're going to use based on the table. If it was moving constantly, we would have used kinetic friction. So we're going to go ahead, we have a new block, 1.5 kilograms. We're going to have to find the normal force. So we're going to do the weight equation. And when we get the weight, 1.5 times the acceleration due to gravity, we get 15 newtons of weight. And that will be, so weight down equals normal force up. Once again, we're just looking at the magnitude. We're going to have 15 newtons of normal force going on. So we're going to go to our equation, and we're just asked for what's the minimum force. So we're going to use that as our normal force. We're going to go ahead and use this as our static friction because we determined it would have to be static friction based on the scenario here. And we get 3.75 newtons. Now that would be the force of friction to that you'd actually slightly have to surpass. So maybe 3.75. 0.00001 would be a better answer, but I would just take this for a test or quiz or anything. You'd want to give me 3.75 newtons as your answer. How much force would it take to keep the 1.5 kilogram block of wood moving at a constant velocity after it's moving? So to keep it moving after it's moving, and once again, you're going to look, it's wood, and it's still the wood on wood thing from before. So it's still just a continuation of the last problem. But now we're going to keep it moving at a constant velocity. So we're going to go ahead and use the kinetic friction there. We still have the normal force from before, and we're going to use our coefficient of, or our force friction equation. And we're just going to plug in the kinetic friction because we're keeping it moving. So it's moving this whole time at a constant velocity. We're not looking at acceleration. This is still dynamic equilibrium. So whatever we're applying, since it's constant velocity, the force of friction that we solved for would be equal to. We use our values there, 0.2 and 15, and we get 3 newtons of frictional force. So this is going to be the force pushing back against your motion, creating this constant velocity. 14. Would a 15 kilogram brick at rest on wood floor accelerate when 120 newtons of horizontal force is applied? So this is actually important. You have to, you're asked if it would accelerate. Because it's at rest, you want to take a look. It's wood on brick, wood, not that wood, that wood. wood on brick, and we're going to go ahead. So we have wood on brick, and it's at rest still. So we want to make sure that it can break through with this and break into kinetic friction first before we do anything. So we're going to use this force of, or with the coefficient of static friction. We're going to have to figure out a new normal force because they gave us kilograms here, not weight. So we got the 15 kilograms, we got the 10, we get a normal force equal to the weight of 150 newtons. So normal force would be 150 newtons, but we're going to go ahead and use the force of friction equation. We're going to use the 0.6 for our coefficient of friction. And when we do that, we're going to get a frictional force of 90 newtons. So if the frictional force is there of 90 newtons, well, this 120 newtons is going to be greater than 90 newtons. So we know that it's going to accelerate. And in fact, in the next part, we're not going to use the 60 anymore, because once it's moving, once it already starts moving, which it would, because this 120 is greater than the 90, with the frictional, and they tell you the 120 is what you're applying, we're going to have kinetic friction going on. So we'll go to this problem. What would, and you already see the answer, I need to go fix that later on, didn't mean you to see the answer. What would a 15 kilogram brick on a wood floor accelerate at when 120 newtons of force is applied? So we have 120 newtons of force. Well, we have our normal force we figured out in the last question. But we're going to go ahead, and we know it's already moving. So in order to figure out how much it's accelerating, since it's already moving and it's wood on brick, we're going to go to this value for our coefficient of friction, because it's wood on brick and it's already moving. And so now we can determine how much force back there is. And we determine how much force back there is by taking the coefficient of friction times the normal force. We get 67.5 newtons of force backwards. But we're applying 120 newtons forward, so we get the overall 120 is bigger. We subtract the 67.5. The 120 was forward. In this case, I didn't tell you right or left, but here it would have been forward, or if you're looking at this animation or this picture, it could be right. But 52.5 newtons is the force forward, the net force when you put these together, and that net force is what's going to cause acceleration. So this F net equation rearranges to this equation, and when you plug in the values, 52.5 and 15, you get 3.5 meters per second squared. So the key here is we checked in the last problem to see if it was moving. And then after we know it's moving, because this is bigger than the static frictional force, then we can go and take the next step and actually see how fast it's moving. But we had to go to the kinetic friction because it was already moving. We didn't want to use static friction because this is just telling you if it's going to start. This is telling you after it's moving how much it's going to accelerate, or how much friction there is, which you can use to determine if it will accelerate. Okay, so now we're going to go ahead and we're going to take this a step further, and we're going to go ahead and we'll solve for an acceleration, and we'll plug this into one of these equations because we'll have more information so we can solve for another variable. So this is the tying it to the 1D motion. 81 kilogram person runs and slides. The coefficient of friction, kinetic friction between the person and the ground, because he is moving, is 0.72. So you don't need to know anything else. There's no static friction going on here. What's the magnitude of the frictional force? So we're going to start off, we're given mass, so we're going to have to figure out the normal force. We're going to take the mass of 81, we're going to multiply by the g of 10, and we get a weight of 810 newtons, but of course it's a horizontal surface, or it's the ground, and we're assuming it's a horizontal surface. We're going to get a normal force of 810 newtons. Now we want to go ahead and figure out what's the frictional force that's going to be between this person who has a normal force of 810 newtons, the ground causing that, and with that coefficient of friction of 0.72. So we just plug this in, and we plug this in, we multiply it together, we get 583.2 newtons backwards. Backwards is going to be important for the next part. So I've been leaving that off a little bit, but it's going to be a negative because we're going to be going and we're going to be sliding and we're going to be slowing down. The force is backwards, the net force is, the acceleration is going to be backwards because the net force is backwards. That'll be important with our next question right here. So now we're giving you information. We're looking at everything else. The person's initial speed. What was the person's initial speed? That's what we're looking for. It took 2 seconds to come to rest, and we solved for that force of friction, that 583.2 newtons backwards. So we have a net force, which equals mass times acceleration. This frictional force is the only force that's involved when this person's sliding. We're going to use that. And we're going to use that to figure out, and again the mass to figure out our acceleration. So there's that negative force, and once again I'm going to go ahead and take that negative, I'm going to plug it in front of this, and we're going to have a negative number so we can see what negative acceleration or deceleration is occurring. So we have that 583.2 negative 583.2 divided by the 81 mass. Once again, we're using mass, not weight down here, or normal force down here. And we plug that in, we get an acceleration of negative 7.2 meters per second squared. So now we're going to go ahead and take that to the next step. They ask us for the initial speed. They tell us, well, they don't tell us, they give us other information which allowed us to solve for the acceleration or deceleration. We know the person's going to come to rest. They're going to slide to rest. And we know it takes 2 seconds. So this will lead us, if you look at your 1D acceleration equations, you'll find this equation works perfectly. You have your VF, you have your VI, you have your A, and you have your T. And that includes our unknown. We always want to make sure we have our unknown in there, or else you can't pick the right equation. So we'll plug in our values, and we get, when we do this, this is going to be 0 equals VI plus, this would just be minus 14.4 when you multiply these two together. So you're going to have to add the 14.4 to both sides. And when you add the 14.4 to both sides, that gets rid of this, and you end up getting VI equals 14.4, which is what I have here. Doesn't matter which side the VI is on, but it's the same thing. I say 12 is a dozen, or a dozen is 12, but they're both true statements. Okay, so lastly, the last problem that I want you to look at right now is, let's take a look. There's a situation where a person is applying a force. Often you're pulling something, and you're not pulling it directly horizontal because it's just a weird angle. So you're going to pull, maybe use a rope, and you use the tension in a rope and pull an object at an angle to try to get it to move. Well, what you're doing when you pull it up at an angle is you are decreasing the amount of normal force. You're decreasing the amount the ground has to push up. The ground has to push up less because you're actually going to be applying a force as well. So you're helping the ground out. You're going to figure out a value that you're going to decrease normal force by, and that's going to be this value. Another thing is that this object's going to be moving to the right, so therefore any upward force is not going to change the acceleration of this object. The only thing that's going to go into acceleration is going to be this side right here. So using this information that we have here, we can figure out how much is the normal force going to be relieved and how much force is going into the acceleration itself that friction is going to work against. So let's go ahead and try a problem. And a 5 kilogram box is pulled at an angle of 25 degrees from the horizontal with a force of 75 newtons. If the coefficient of kinetic friction is 0.25, what is the normal force? So we're going to calculate the weight. We have the box, which is 5 kilograms. We have our acceleration due to gravity, which is 10. So our weight is 50 newtons, but not the normal force. So not the normal force, because we're going to have this component that's going to decrease it. So what we have to do next is we have to figure out, well, what's this force? What's this side that's going to be pulling up so the ground doesn't have to pull up as much? So we take the opposite side as the sine of the angle. Make sure you are in degrees, not radians in your calculator. And we have our hypotenuse, which we were given there. And so we can plug these values in, and we find out that the ground, or we are pulling 31.7 newtons of force upwards. And so because we're pulling the 31.7 newtons of force upwards, the ground's not going to have to do as much work to push it upwards. So we take the 50, the weight is pushing down by 50 newtons. We are pulling up by 31.7 newtons. So the ground only has to do a little bit left over. The ground only has to push up. Once again, that's the term normal force. The ground only has to push up by that 18.3 newtons as a result. So this is going to be the force that goes into the actual friction, because there's not going to be as much interaction or pushing against the ground because you're pulling up and kind of relieving that a little bit. Okay, so let's go ahead and what is the applied force? So before we do, we're kind of working through a single problem, but I'm stepping you through column 18, 19, 20 through 22. This could be all combined in one problem where you'd have to do these steps and realize which order you have to go in. So now we're going to figure out, well, let's go ahead and figure out what force is going into motion, and that's going to be this force right here. So this is the adjacent side of from the angle, we have our hypotenuse. And so we're going to go to adjacent equals cosine 25 times 75. Adjacent equals cosine of the angle times the hypotenuse, which we have here. And we get 67.97 newtons forward. So we're pulling. This is the force that's going to go into the motion, but we're going to have a frictional force. So this 69.72 is right here, but we are going to have a frictional force that we'll have to solve. And that's what I have to do in the next step. So we're going to solve for the force of friction. We're going to use our normal force from before. We're not using the weight because once again we are relieving some of that weight. We're going to use our coefficient of friction that they gave you because it's kinetic, they're moving. And we just go to our force of friction equation using the kinetic friction, so therefore we're going to have the force of kinetic friction. This is everything we need. We plug in our values and we get a force of friction of 4.58 newtons. So now we know we have a force of 4.58 newtons backwards. Now we can go ahead and answer 21. What is the net force, which is going to go into acceleration? So if there's 67.97 newtons forward and there's 4.58 newtons backwards, we can kind of put that together. We can say forward is positive, we can say backwards is negative, and we subtract the 4.58 backwards, and we get 63.39 newtons forward. So this is the net force that will create the acceleration on this 5 kilogram object. And so now we're ready for our last question, which is going to be right here. And what is the acceleration as a result? So with a net force of what we just solved forward and a mass of that 5 kilograms, we can solve for acceleration going to our net force equation, F net equals ma, which rearranges to this, and we get 63.39 divided by 5, which is 12.68 meters per second squared. So the very last question I have here, I didn't really mean for you to see this animation, but you can see it in this animation. If you lift the side of a desk, increasing the incline, so you have static friction increasing, and then all of a sudden you break into, what's happening is as you increase the incline, the force that the actual hill is applying downhill increases. Well, once it breaks past the static friction point, the kinetic friction is always less than static friction. So it's still at that same incline, so there's still going to be that same downhill force, and we'll see this incline and a little bit more about it in a future lesson. But the force uphill is going to be, the force of friction is going to be now kinetic. So this is what was required to break the static friction. This is the kinetic friction, so this is going to be less than that, so therefore net force is going to be downhill, and therefore you're going to have an acceleration as a result. So the block would accelerate down the incline. And that's it.